Last time we looked at bioinorganic chemistry, where we said it is concerned with the function of metallic and non-metallic elements in biological systems. We went further to look at the factors that led to increased interest in this branch of chemistry, where we said it is because of the improved analytical methods, less time-consuming preparative techniques, increased concern about environmental hazards, and also use of metal complexes as the therapeutic agent. We gave an example of iron salad, which cures anemia when fed to a person who is anemic. It improves on the formation of hemoglobin, hence curing anemia. We said the essential elements, there are about 40 elements, of which 25 are proved to be essential to living organisms. And we are classified into 3 categories. We have those which are required in larger quantities, referred to as macronutrients, and those which are required in smaller quantities, referred to as micronutrients. And then the last category are those which are incorporated into organic molecules. We looked at the essential elements, their importance in biological systems, symptoms, and the source where we can obtain them in case of deficiency. Today, we are going to look at metalloenzymes or metallocoenzymes. These are enzymes with a strongly bound metal ion, in which the metal ion is an essential participant in the catalytic process. An example is zinc metalloenzymes, which catalyze peptide hydrolysis and maintain the bicarbonate and carbon dioxide equilibrium. The point to note here is that metals do not exist as free metal ions in a living system, but as metal chelates of exceptionally high stability. The assignment I can leave you with today is discuss the role of metal chelates in living systems. Harmful effect of excess metals on the human body. Do metals have harmful effect? Yes, though smaller quantity of metals are useful for the normal function of human body. However, if they are in excess, they can lead to, or they can be harmful. An example is the iron. We said the intake of iron increases the formation of hemoglobin and cures the disease known as anemia. But in excess, it can cause a disease of cinderosis. This disease has been found in the Bantu tribe in Africa because they prepare their beers in iron pots, which increases the intake of iron in their bodies. Another example is copper. Copper metal required for normal man is about 0.1 to 0.15 grams. But if in excess, it can lead to a disease known as Wilson's disease. And the symptoms for these, a patient feels nervous disorder. He has got difficulty in swallowing and also experiences steel joints. Nanometals. There are about 6 important nanometals, which include carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These elements make up the molecular building blocks of living matter. That is, they are responsible for structures of sugars, amino acids, purines, fatty acids, pyridine, and nucleotides. These molecules have independent biochemical roles, and they are constituents of large molecules such as glycogen, starch, proteins, lipids, and nucleic acid. Complexing characteristics of trace metal ions in biological systems. We have the metal and the preferable ligand. Manganese prefer to bond with oxygen donors. Iron prefers oxygen donors, nitrogen donors, and sulfur donors, while cobalt prefers oxygen donors and nitrogen donors. Copper prefers nitrogen and sulfur donors. Zinc prefers nitrogen and oxygen donors, and molybdenum prefers sulfur donors. To understand the metal ligand bonding, Pearson suggested a simple rule known as Pearson's Principle, called Pearson's Principle, and is known as hard and soft acid and base principle. This principle states that hard acid prefer to combine with hard bases, and soft acid prefers to combine with the soft bases. This combination gives rise to the formation of a stable product. In the presence of a hard acid and a soft base, there is either formation of a weak bond or the bond never forms at all. You have to be careful. Most of the students use strong acid and strong base, or weak acid and weak base. Please don't use that. We have to go with the Pearson's Principle. You have always to mention hard acid, or to use hard acid to prefer to bond with hard bases, or soft acid to prefer to bond with the soft bases if they are to form a strong, a stable product. Classification of lowest acid, lowest bases into hard, soft, and borderline acids and bases. The lowest acid. Characteristics of hard acid, soft acids, and borderline acids. The hard acids have got acceptor metal atoms of smaller size, while the soft acid have acceptor metal atoms of larger size. The hard acid have acceptor atoms with a high positive charge, while the soft acid have acceptor atoms with low or zero positive charge. Hard acids, their valence electron cannot be polarized or distorted or removed easily, while for the soft acid, the valence electrons can be polarized. For borderline, the characteristics of the borderline acid are intermediate between those of the hard acid and the soft acids. Examples of hard acids and soft acids and borderline acids are highlighted in the table. Pause and read. Let us look at the lowest base, the donor or the ligands. Characteristics: hard base. The donor atoms of the hard base has higher electronegativity, while the soft base has low electronegativity. The hard base holds its valence electron strongly and hence cannot be polarized, while the soft base holds its valence electron weakly and hence can be polarized easily. The hard base has filled orbitals, while the soft base has partially filled orbitals. The borderline bases, these have got intermediate properties between hard bases and soft bases. Again, the examples are given in the table You can pause and read more. Therefore, from those two tables, we can conclude that there are about 4 factors that affect the hardness of the acid and bases, and these include the size, charge, electron configuration, and the nature of the attached group. So next time, we are going to look at the application of the HSAB theory to biological systems.